In this video, I'm going to talk about the convolution integral. Okay, I'll give you very short discussion. Okay, so why do we need convolution? Sometimes, because when we solve a differential equation by Laplace transform, what we do is we take the Laplace transform first, and then we solve for Laplace transform of y, and then we take the inverse Laplace transform, right? When you take the inverse Laplace transform, the method we learned so far is we will have to do the partial fractions and separate the function into the simpler functions so that we can find out the inverse Laplace transform of each of the fractions there, right? But sometimes it is hard to get the partial fraction, or it is long or more complicated to do the partial fractions, or sometimes it will be easier to take the inverse Laplace transform of a function by the convolution method than the method of the partial fraction. Okay, so we will see some examples, but for now let us define what do we mean by convolution. Okay, so for functions f and g that are piecewise continuous in an interval 0 to infinity, the convolution integral of f and g is defined by, okay, the convolution integral is denoted by f star and then g, and this is given by the integral of 0 to t f t minus tau and g tau d tau. Okay, so basically what we do is, basically you can see that the function, one of the function f is shifted right by tau units, right, and then times g tau, and the product of that will be integrated from 0 to t. Or you can do f tau and then shift the function g with tau units right. Okay, you can think that way. The product is integrated from 0 to t. Okay, so basically this, it will be a function of t, because you see that you will be integrating with respect to tau and then replace tau by 0 and t, so ultimately you will get function of t. Okay, so this is the definition of convolution integral. You can use this one or that one, either one. Okay, now what are the properties of the convolution integral? The number one property is the convolution integral is commutative. Convolution is commutative, meaning f convolution g is equals to g convolution f. Okay, next it is distributive over the summation. That means f convolution g1 plus g2 equals to f convolution g1 plus f convolution g2. Okay, so convolution is not really a product, but it is the integral of the product when one of the function is shifted a little bit. Okay, you shift one of the function a little bit, tau it away, and multiply with g and take the integral. This is basically a convolution. Okay, similarly, the third property is f convolution g convolution h is equals to f convolution g and then convolution h. And if you want to find out the convolution of f with 1, that will be 0 to t f u du. How come that happened is because if you replace that by because this one will be 0 to t and then f of t minus tau, right, and then g tau is just 1, right, and then d tau, right, you see that. And if you replace t minus tau by u, you will get d tau equals to minus d. So and then if you change the limit of integration, right, so when tau equals to 0, then u equals to t, right, equals to t, and when tau equals to t, then u equals to 0. So what you get basically is that integral look like t to 0 f of u du and then negative sign, right? But when you swap the lower and upper limit, you will get positive, right? So it is 0 to t f of u du. This is how you get that. Okay, so the convolution integral of a function f with 1 is basically same as the integral of the function from 0 to t. Okay, so the next thing we are interested is the Laplace transform of the convolution integral. The Laplace transform of the f convolution g is equals to the simple product of their Laplace transform. Okay, so basically convolution integral is the one that has the Laplace transform as the product of the separate Laplace transform. You see that the Laplace transform of the convolution is equals to Laplace transform of the f times the Laplace transform of the g. So separately you can find the Laplace transform separately and multiply that. That will give you the convolution, the Laplace transform of the convolution, right? Let us denote that Laplace transform of f is f uppercase f function of s, and then Laplace transform of g is uppercase g s. Then the other way is, if you take the inverse Laplace transform, then what do you get? The inverse Laplace transform of fs times the gs is equals to basically the lowercase f convolution g. Okay, so let us see some examples on how do I use convolution to find out the certain Laplace transform of the certain function. Okay, and then I will give you another example. How do I use convolution to solve a differential equation as well? So let us do this example. Find the Laplace transform of 0 to t at 4 times t minus tau and e to the negative 2 tau. Okay, how do I do this? So let us use convolution to do this one. So solution is, I want to do f of t is 4t, and then I want to do g of t is e to the negative twice t. Then what will be f convolution g then? Then f convolution g will be 0 to t, and then it will be f of t minus tau, right? So it will be 4t minus tau, right? And then times e to the negative 2 tau, that is g tau, and then d tau. Basically f convolution g is that thing, right? Now we want to find out the Laplace transform of that integral, meaning this integral. So which is same as finding the Laplace transform of f convolution g. So the Laplace transform of f convolution g equals to, what is the formula? It is Laplace transform of f and then times Laplace transform of g. You see that? What is the Laplace transform of f? It is 4 times the Laplace transform of t is 1 over s square, right? So that will be 4 over s square times the Laplace transform of g is e to the negative twice t. So the Laplace transform of g will be 1 over s plus 2, right? You see that? Why is that? What is the reason for that? It is, we know that Laplace transform of e to the negative at, right, times f of t is equals to how much? It is f of t minus a t plus a, right? Or if there is a positive at ft, it will be t minus a, but it is f of t plus a. What does that mean? Meaning that you find out the Laplace transform of ft and replace that t by t plus a if there is minus, and t minus a if there is plus. Okay, so here what is the gt is e to the negative twice t, that can be written as negative twice t times 1, right? So what? How do I find out the Laplace transform? It is 1. The Laplace transform of 1 is 1 over s, right? But that s should be replaced by s plus 2. You see that? So that is basically 4 over s squared times s plus 2. You see that? This is the Laplace transform of f convolution g, or the Laplace transform of this integral. Let us see one. So the example is, find the inverse Laplace transform of s over s plus 1 s squared plus 4. You remember that the one way of finding the inverse Laplace transform is you use the partial fraction, right? You do a over s plus 1 plus b s plus c over s squared plus 4, and you combine and find out that. So the other way is we use the convolution. Okay, so solution is to solve this, or to find out the inverse Laplace transform. What we do is we know that you can write s over s plus 1 and then s squared plus 4, okay, can be written as 1 over s plus 1 times s over s squared plus 4, right? We know the inverse Laplace transform of this separately, and we know the inverse Laplace transform of this separately. Let us do that as f of s times g of s, because we know they're separate inverse Laplace transform, okay? So we don't have to do the partial fraction for this kind of function. What we do is so inverse Laplace transform of f of s times g of s is equals to what? It is f convolution g, right? Which is same as 0 to t f of t minus tau, right, times g of tau d tau. But what is f? F is the inverse transform of uppercase F, and then the G is the inverse Laplace transform of uppercase G. That is where F of t is equals to inverse Laplace transform of F of S, which is the inverse Laplace transform of 1 over S plus 1. So how much is that? That is e to the negative t, right? Similarly, G of t will be inverse Laplace transform of G of S, right? So that will be inverse Laplace transform of S over S square plus 4. So how much is that? It is cosine. So this is basically cosine twice t, right? Cosine twice t. Because the Laplace transform of cosine at is S over S square plus A square. So since it is S over S square plus 4, so A is basically 2. So it is cosine twice t. Therefore, that inverse Laplace transform of F of S times G of S is equals to 0 to t. So you will get e to the negative t minus tau times cosine 2 tau and then d tau. You see that? Now this one, for this one, see, so e to the negative t and then plus tau, right? This can be written that way. So what you can write from here, which is equals to e to the negative t. I am pulling that outside because this is with respect to tau, so t we can pull that outside. You will get e to the positive tau times cosine 2 tau d tau. Okay. Okay, so to find out this integral 0 to t, okay, to find out this integral, what we do is we basically use that formula, e to the integral of e to the at cosine bt equals to 1 over a square plus b square, e to the at times b sine bt plus a cosine bt. Let us use that formula. What do you get? There is e to the negative t already there, right? So 1 over a square plus b square is, a is basically 1, b is 2, right? So 1 over 5, and e to the positive t, you can write e to the tau, right? Because there is d tau there. So e to the tau, right? Let me write down this way so that I can plot the limit later for this. And then 2 sine twice tau plus cosine twice tau. You see that? And then the limit are 0 to t. Now what we do is we will plug in t. You will get e to the negative t times 1 over 5, right? You will get, when you plug in t, you will get e to the t 2 sine twice t, right? And then plus cosine twice t. You see that? From here. And then minus, plug in 0. You will get e to the 0 is 1. So that is 0. So it will be negative 1. You see that? Now what do you get? You will get basically, let's distribute this to that. You will get 1 over 5, right? If you distribute this to both of these terms, you will get e to the negative t and e to the positive t will cancel out. So 2 sine 2t plus cosine 2t, right? Minus e to the negative t. This is what you will get, okay? So basically that is the answer for the inverse Laplace transform of this function. Okay, so basically when you take the inverse Laplace transform, sometimes the convolution helps. Sometimes the convolution is easier than the partial fraction method. Okay, so let me write a note here. So note is the convolution integral is useful when the forcing function is not specified. What does that mean? That means, for example, suppose you have a equation like 4y double prime plus y equals to gt. the particular value of this gt function is not given, with y of 0 is 3 and y prime of 0 is let's say -7. Suppose you have this equation and you want to solve this equation, okay? So how do I solve this one then? So let us see the work for that, okay? If you want to solve this equation, then what do is you just use the Laplace transform, okay, and then just do all those things that we used to do to solve a differential equation. So we take the Laplace transform and then we solve for Laplace transform, right? What do you get is, when you solve for the Laplace transform, this is what you get. Laplace transform of y for this equation will become like this: 3s minus 7 over s squared plus 1/4, okay, that's what you get, and then plus gs over 4 times s squared plus 1/4. This is what we'll get, okay? So what is gs? Gs is the Laplace transform of gt, okay? Now we will take the inverse Laplace transform on this. Now let us take the inverse Laplace transform. Inverse Laplace transform. When you take the inverse Laplace transform, what do you get? So on the left hand side, you will get yt. You see that? Equals to, on the right hand side, what do you get? If you take the inverse Laplace transform of this is what you will get. 3, you will have to split that, okay? 3 and then cosine t over 2. Cosine t over 2, right? Because you will have 3 s over s squared plus 1/2, and that will be inverse Laplace transform of that will be 3 cosine t over 2, and then -7 over 2, 7 over 1/2, that will be 7 times 2, right? 7 over 1/2 times, that will be 1/2 over s squared plus 1/2 square will be sine t over 2. So this will be 14 later, okay? And then plus, for the first term, right? And then plus, what do you get for the second term is, you will get inverse Laplace transform of 1/2 g of s times 1/2 over s squared plus 1/4. That's what you will get, right? Because I'm taking the inverse Laplace transform of that term. You see that? So what that happens is 3 cosine t over 2 minus 14 sine t over 2, right? Plus, so this is that 1/2 will come out. 1/2 will come out. And then what is this? This is basically gs. So you can say inverse Laplace transform of g of s times, you can say f of s, right? What is f of s? F of s is this one. You see that? So f of s is that one. So this is the inverse Laplace transform of gs times fs. You see that? So what is the inverse Laplace transform of gs times fs? That will be basically f convolution g, right? For this term only. F convolution g. But what will be f? F will be the inverse Laplace transform of that. That will be sine t over 2, right? So this becomes 3 cosine t over 2. You see that? Minus 14 sine t over 2, right? Plus, you can write 1/2 and then 0 to t. You see that? Basically sine tau over 2 times g of t minus tau, right? And then d tau. Look at that. This is the solution. Y of t. This is the solution of that that equation, that differential equation. So this is how you solve a differential equation by using the convolution integral. Basically, convolution integral is very useful when you are trying to find out the inverse Laplace transform. Okay, guys? Alright, so this is the end of chapter 5. Okay, so the next thing I will post some videos on how to solve a differential equation using the numerical method. Okay, meaning that not all of the differential equations solved by using the method that we have learned so far. So many differential equations cannot be solved by the methods we learned. So in that case, we use the numerical method. Okay, so I was planning to do all these numerical method thing in the MATLAB, but since we don't have the classes, face-to-face class, so I will show you how to do that theoretically, and then I will present the MATLAB as well. Okay.